In this example problem, we are looking at a birdhouse that is hung from a horizontal pole by 3 wires, and we are asked to find the tension in each of the wires. So the wires are labeled A, B, and C, and the tension in each of these wires I am going to call FA, FB, FC. There are 2 themes of this problem that I'm going to mention. The first is we're going to be investigating the concept of the tension force. So we said tension is a force of a rope or cable or string or similar device, and ropes have the property that they could only pull, they cannot push. So the way I think about this scenario is I see, for example, rope A. Rope A is somehow attached to the horizontal pole. So rope A is pulling on this horizontal pole in this direction, that is down and to the right. But simultaneously, rope A is also tied to the other ropes. You could imagine maybe there's a knot or a metal ring or something that they're all tied to. And simultaneously, rope A is also going to be pulling up and to the left on the other ropes. Now, the rules for the tension force are the amount of tension in a rope is the same at every location in the rope. So the down and to the right tension force on the horizontal bar is going to be the same strength as the up and to the left tension force on the ring or knot on these ropes. The other rule about tension is tension force can only pull, it cannot push. So I just ask, well, if I'm pulling on the knot, that means I'm pulling up and to the left. If I'm pulling on the bar, that means I'm pulling down and to the right. And that tells me something about the direction of the tension force. The second theme of this problem is that Newton's second law, F net equals ma, is really 2 equations disguised as one. By that I mean, if I write F net equals ma as a vector, because F net is a vector and because A is a vector, these are really 2 equations. I have one set of equations for the x direction, F net x equals max, and I have a second set of equations for the y direction, F net y equals may. Now, for the first part of this problem, we're not really going to see this, but for the second part of this problem, when we're working through it, this will be very important. And in principle, I could have different numbers for some of these quantities. The mass of my object is going to be the same. That won't be very important. But the acceleration, in principle, could be different. The forces themselves, the components of the forces could all be different numerical values. So to begin this problem, we are told that the birdhouse is not moving. Not moving is an example of not accelerating. It is not the only possible example of not accelerating, but it is one example of non-acceleration. So if we know that nothing is accelerating in this problem, I could write that as A is equal to 0, and specifically I could write that as AX equals 0 and AY equals 0. That implies that the sum of all forces must also be 0. So F net x equals max and F net y equals may. And we said if AX is 0, that implies the sum of all the forces in the horizontal direction must add to 0. And if AY is 0, the sum of all the forces in the vertical direction must also add up to 0. So we want to find the tension in each of the cables that is holding up the birdhouse. We are given the mass of the birdhouse as 5 kilograms and the angles of cables A and B. Cable C is assumed to be perfectly vertical. So let's go on and find out the tensions in these cables. The first thing I'm going to do for this question is I'm going to look at part of the problem. I don't need to look at the entire problem all at once. Let's just see, is there anything I can look at and have just one unknown for? And I look at this problem and I say, let's focus on the birdhouse itself. So let's just look over here at this part of the problem. So in this part of the problem, I could redraw it as having a birdhouse hanging from a cable. Here is cable C, and then here's my birdhouse that is 5 kilograms. Now I ask myself, what are the forces acting on this birdhouse? Well, we know the Earth exists, so there is a force of gravity, and that force of gravity is going to pull the birdhouse straight down towards the center of the Earth. So there is a force of gravity pulling down on the birdhouse. I'll write that as FGR for F gravity. And there is an upward force because cable C is attached to the birdhouse, and ropes only pull, they cannot push. So in this case, if the rope is exerting a force on the birdhouse, that force must be along the cable. So the tension in cable C on the birdhouse is going to be straight up. So I'm going to call this the force in cable C. And FC, as I said, is a tension force. Now I look at this question, I could ask myself, are there any other forces on the birdhouse? Well, we accounted for the tension in the cable, we accounted for gravity, we assume there's no wind, anything like that. So we have now successfully accounted for all the forces. And I look at this problem and I notice there really are no forces in the horizontal direction in this particular window of the problem. Later on, when we look at the cables A and B, we will need to account for horizontal and vertical components of force. But for now, we could have everything be we could look at everything only in the vertical direction. So I'm going to write down what I know. I know I'm only working in the Y direction. For the moment. And I know the acceleration in the Y direction is 0. I know gravity is entirely in the Y direction, and the force of gravity in the Y direction, FGR comma Y, is going to be negative mg, which is negative, the mass of the birdhouse is 5 kilograms, and g is 9.8. So the strength of the gravitational force is 5 times 9.8, and I have this negative sign because gravity pulls straight down. Now I have the tension force in cable C. Right now, you might look ahead and be able to see what it's going to be, but right now I'm going to say I do not know what this tension force is. So I will write the force of tension in cable C in the Y direction. I'm just going to write that as FC. And here FC is going to be a positive number because the tension is pulling upward. So what I'm going to do is I'm going to take these 3 pieces of information and I'm going to insert them into Newton's second law. So Newton's second law, acting on the birdhouse, could be written as F net Y equals MAY. Okay, let's write out what all these forces are. F net is the sum of every force in the Y direction, because I'm looking specifically at Y. I have 2 forces right now I'm considering, the force of gravity in the Y direction and the force of tension in the Y direction. So I would write F gravity in the Y plus F tension in rope C in the Y direction equals mass times acceleration in the Y direction. So I look at the table of everything I wrote down. Force of gravity in the Y direction is negative 5 times 9.8. Force of tension in rope C in the Y direction is FC. Now the mass of the birdhouse, we were told the mass of the birdhouse is 5 kilograms, and the acceleration in the y direction is 0. So at this point, I have the tension in rope C is my only unknown, and I could solve for the tension in rope C. So I get negative 49 plus FC is equal to 0, and so I get the tension in rope C is 49 newtons. Okay, so we have found the tension in one of the ropes. Now what we're going to do is we're going to need to look at a different part of the problem to find the tension in the other 2 ropes. So previously we asked about the forces that are pushing or pulling on the birdhouse. We got some piece of useful information. There is an upward force on the birdhouse due to rope C. Now for the next part of this problem, I'm going to, instead of looking at this part of the birdhouse, or instead of looking at this part of the picture with the birdhouse, I'm going to look at this part of the picture right here. So right where the ropes meet. You could imagine, as I said, maybe there is some ring that all the ropes are tied off to or something, and they're all pulling in their respective directions. Or a knot or something, if it helps you get a visual mental picture of this problem. So I'm going to draw this picture now, and now we're going to have to look at forces in 2 different directions. So let's say here is a ring where the 3 ropes meet. I have rope A coming out this way, I have rope B coming out this way, and I have rope C coming downward. So here is rope B, here is rope A, and here is rope C. Now what I'm going to do is I'm going to remember that ropes only pull, they cannot push, and I'm going to ask myself, what is the direction of the force that the ropes are pulling on the ring? Well, if ropes can only pull, that means the force of tension from rope B is going to be up and to the right. So here is my force of tension from rope B. I'll write it up here, FB. I have the force of tension from rope A is up and to the left. So here is the force of tension in rope A, FA. And then rope C is pulling down on the ring. So force of tension from rope C is straight down. And here is FC. So this is an example of something we talked about before. Rope C is pulling up on the birdhouse. Rope C is pulling down on this knot or this ring in the center where the ropes are all connected. This is okay. Rope C is pulling in one direction on one object, but if we change the object that we're looking at, it is possible for the rope to pull in a different direction on that other object. So the next thing I'm going to do is, and I think this is something you should do for every force problem that involves 2D, is you should break all of these forces into their components. So I look at this picture of my forces. I am going to choose to put my origin right at the center. So here's my origin. So X is going to come that way, and Y will go straight up. And I want to break all of these forces down into their components. So, okay, I look at the original picture. I am told this is a 20-degree angle. And if I remember from geometry, if you have 2 parallel lines and then you intersect them with a third line, something like this angle over here will be the same as that angle down there. So if this angle is 20 degrees, this angle must be 20 degrees as well. So I could compare this picture to this picture. I'll get rid of this box to make this easier to draw. I'll just draw a second horizontal line. And now I could say if this angle is 20 degrees, this angle must be 20 degrees also. And if this angle over here is 40 degrees, I could say this angle over here must be 40 degrees as well. So I compare what I drew here to the picture I have over here. I could say this angle is 40 degrees, and this angle right over here is 20 degrees. Now, what I'm going to do is I'm going to break down all of these forces into their components. The first force I'm going to break into its components is the force of tension in cable C. The reason I'm going to do that force first is because it is going to be very easy to do. I look at the picture, I notice this force is not at all in the left-right direction. So I could say the force of tension in cable C in the X direction is 0. The force of tension in cable C in the Y direction is negative 49. This negative number is important because down means negative, and that is different from up. So we found the tension in cable C previously when we were looking at the birdhouse, and we reminded ourselves that the tension is the same everywhere along a cable. So if I know the tension in the cable down here, it must be the same as the tension up here, which is 49 newtons. Next, what I'm going to do is I'm going to find the force of tension in cable B. So I'm going to draw a picture of this. Let's draw this as, here is my X and my Y axis again. I'm just redrawing this picture to make it a little bit neater. Here is cable B, so I'll call this FB as a vector. I do not know how strong this force vector is right now. So I'm going to say the strength of this force vector is FB. The magnitude of the force vector is FB without the arrow as a hat. The force itself does have the arrow as a hat. We also know that this is an angle of 40 degrees. So even though I don't know the strength of this force vector, I could still say something about it. I could still say that FB in the X direction is going to be FB cosine 40. And if I put that in a calculator, I will get FB cosine 40 is equal to 0.77 FB. And I could say FB in the Y direction, FB comma Y, is FB sine 40. And when I put this in a calculator, I get the force of tension in cable B in the Y direction is 0.64 FB. I'm going to do the exact same thing for cable A. The only difference is cable A points off in the second quadrant, so I need to be careful. I'm not going to say cosine and sine of 20 degrees. I'm going to say cosine and sine of 160 degrees. So the picture we have for cable A is going to be, here is the X and the Y axis. Here is the force of tension in cable A. And this is force vector FA. Force vector FA has magnitude FA without the hat. And we were told that this angle right here is 20 degrees. If this angle is 20 degrees, that means this angle from here to here is going to be 160 degrees. So I could say the force of tension in cable A in the X direction, FAX, is equal to FA cosine 160. And if I put that in a calculator, I get FA cosine of 160 is negative 0.94 FA. And the force of tension in cable A in the Y direction will be FA sine 160. And if I put that in calculator, sine of 160 is going to be 0.34. So I get 0.34 FA. So let's look at what we've done here. Everything I have on the board right now is just breaking these three force vectors into their x and y components and getting it in as few unknowns as possible. Now, I know the total amount of tension in cable C, and I know the direction of cable C. So because I have those two pieces of information, both the strength of the tension and the direction, I was able to give numbers for both of these values. For the other two cables, that was not the case. I know the direction of the force of tension in the cables, 40 degrees and 160 degrees, as drawn here. So I could say something about the direction, but I still don't know the total amount of tension. I don't know the total strength of the tension force, FA and FB, without the vector arrow above them. That's okay. I don't need to know the values. I don't need a numerical value for these yet. I'm just going to write it as much as possible. So here, even though I have four quantities, FBX, FBY, FAX, and FAY, I really only have two unknowns written on the board. One unknown is the strength of tension in cable B. The other unknown is the strength of tension in cable A. So I'm going to write these over here just to make them neat, and then we'll begin setting up a problem and solving Newton's second law. So I have FAX equals negative 0.94 FA, FAY equals 0.34 FA, FBX equals 0.77 FB, FBY equals 0.64 FB, and then we have the force of tension in cable C, FCX equals 0, FCY equals negative 49. So what we're going to do now is we will set up Newton's second law to solve for these unknowns. So the way we, as I said, we think about Newton's second law, we see F net equals ma. But when I write this equation as a vector, this is really two equations in one. I have one equation is F net x equals max, and I have a second equation, F net y equals may. F net y equals may. Two equations. F net x is going to be all the forces in the horizontal, FAX, FBX, FCX. All of those will go in F net x. F net y, FAY, FBY, FCY. All of these will go in F net y. So let's set these equations up. Now, from this problem, nothing is accelerating, so I could also add on to these pieces of information that AX is equal to 0 and AY is equal to 0 in this problem. So for the very first equation here, F net x is FAX plus FBX plus FCX equals MAX. I am being very general right now. F net is all the forces. 0 is an allowed value. And now I'm going to plug in numbers. So FAX, I have negative 0.94 times the total amount of tension in cable A. So negative 0.94 FA. FBX, I look at what I wrote, 0.77 FB plus 0.77 FB. FCX is 0. And then I set that equal to the mass of the ring or the knot where the cables meet. I don't know what that mass is, but it really doesn't matter because AX is 0 anyway. So I multiply it by 0. And when I look at F net X equals MAX, I then could simplify this problem somewhat. I right now have 2 unknowns, but it's going to be okay. When I simplify this problem, I get negative 0.94 FA plus 0.77 FB equals 0. And I am going to rearrange this equation to say FB 0.77 FB is equal to 0.94 FA. And I'm going to solve for FB for the moment. So FB, the force of tension in cable B, could be written as 0.94 over 0.77 FA. So this is going to be one important equation for solving this problem. We are not actually in a position yet to get both the value of FA and FB. As of right now, what we did is we had one equation. Here is our one equation, but we had 2 unknowns. One unknown is FA, one unknown is FB. We cannot solve for 2 unknowns if we only have one equation. But we could simplify it, make a relation between those 2 unknowns. If we really want to find the value of our 2 unknowns, we need a second equation. And that second equation is going to be F net Y equals MAY. So for the moment, I'm going to erase this. I'm going to write this somewhere else up here on the board. And then we'll begin solving F net Y equals MAY. So what we did here so far was we broke down all the forces into its X and its Y components as much as possible. Now, I do not know a numerical value for all these forces, but I can say something because I know something about the direction of these forces, the angle they make relative to the horizontal. I can make some statements about what their X and their Y components are going to look like, even if my knowledge on this is incomplete right now. We consider Newton's second law in the horizontal direction, F net X equals MAX, and from that we found a relationship between the strength of tension in cable B and the strength of the tension in cable A. Specifically, we found FB is 0.94 over 0.77 FA. And if I put that into a calculator, I would find FB is equal to 1.22 FA. So FB is going to be about a quarter bigger than FA. Now, this is one equation with 2 unknowns, and we need a second equation to actually solve for both of the unknowns. The second equation we're going to use is Newton's second law in the vertical direction, F net Y equals MAY. So this is why I feel it is a good practice to write down the components of all the vectors, even if you can't write down a number. Up here for the acceleration, we were able to write a number. For the tension in cable C, we were able to write a number. For the tension in cable A and B, we couldn't write a number. But as much as possible, we tried to write the tension in these different directions. And we just wrote it up to what we know. We don't know the magnitude of the tensions in these cables. So if I now apply F net Y equals MAY, just like before, I am going to pick out, okay, here is Y tension in cable A, here's the Y component of tension in cable B, here's the Y component of tension in cable C, and here's the acceleration of the knot or ring where all the cables are meet. So F net Y, that would be FAY plus FBY plus FCY. All the forces are now accounted for, so I have written everything for F net, and I set that equal to MAY. And now I'm going to plug in numbers. So I have 0.34 for FAY, 0.34 FA. I have 0.64 FB for FBY, 0.64 FB. FCY, we have an actual number for, that's 49 newtons. So because this says plus, this is a negative number, so I'm going to write this as plus negative 49. And then that's equal to the mass of the ring that all the ropes are tied to. I don't know what that is, but again, AY is 0 anyway, so it won't matter that I don't know it because it's going to be multiplied away by 0. So at this point, I now have two equations with two unknowns, and that is enough information to find the total magnitude of the tension in cable A and B. So I could simplify this equation as 0.34 FA plus 0.64 FB minus 49 is equal to 0. And at this point, I now have my two equations with two unknowns that I could solve for. I have this equation right up here that I found from F net x equals MAX. I have this equation down here that I found from F net y equals MAY. So I'm going to rewrite this equation up here and solve the system of equations. And when we do that, we then get 0.34 FA. For the moment, I'm just moving this equation up here so I have more room. Plus 0.64 FB minus 49 is equal to 0. And now what I'm going to do is, well, the force of tension in cable B is equal to this. So I'm going to take this and plug it in right there. And when I do that, I would have 0.34 FA plus 0.64 times 1.22 FA minus 49 is equal to 0. And when I go through, put those numbers in the calculator, I find the force of tension in cable A is going to be 43.75 newtons. After some algebra. And now I have the amount of tension in cable A. I could use either of these equations to find the amount of tension in cable B. If I look at them, this equation is already set up for me to solve for the tension in cable B, so I'm just going to go ahead and do it. So I could say the force of tension in cable B could be written as 1.22 times the force of tension in cable A. We found the force of tension in cable A. It's this much. So 1.22 times 43.75. And if I put that in the calculator, the force of tension in cable B is going to be 53.41. So what did we do here? Well, we now found the force of tension in every cable. We found the force of tension in cable A is 43.75. The force of tension in cable B is 53.41. And the force of tension in cable C we found way back at the beginning of this problem as 49 newtons. So FC is 49 newtons. So at this point in the problem, we are done. We have found the tension in the 3 ropes that are holding up the birdhouse. Let's think about what we actually did in this problem. We said that near the center where the ropes all meet each other, we could imagine that they're tied off to some type of ring and they're all pulling in different directions. Rope C is pulling downward with a force of 49 newtons. Rope B is pulling up and to the right with a force of 53.41 newtons. And rope A is pulling up and to the left with a force of 43.75 newtons. Now, rope C is pulling down on the ring, but simultaneously, rope C is pulling up on the birdhouse. Rope C is pulling up on the birdhouse with a force of 49 newtons, and gravity is pulling down on the birdhouse with a force of 49 newtons. Simultaneously, ropes A and B are pulling up and to the left, up and to the right on the ring that they are tied off to. Ropes A and B would also be pulling downward and to the left and to the right on this long horizontal bar. And I could say, if I wanted to, that rope B is pulling down and to the left on this bar with a force of 53.41. Rope A is pulling down and to the right with a force of 43.75. So if I am talking about the forces on the bar, that would be these 2 forces. If I'm talking about the forces on the ring at the center where the ropes are all tied to each other, I would talk about these 3 forces. If I'm talking about the forces on the birdhouse, I'm talking about these 2 forces. What we did was we said we're going to break every force, every vector in this problem, the forces, the acceleration, into their x and y components. We're going to write out those quantities as best we can. We don't know, as I said, everything about those quantities when we're working through the problem, but we're going to try to put numbers. And if we don't know the strength of the force, we still know something about the angles, so we could still turn those sine and cosine terms into numerical values. We then applied Newton's second law twice, once for the x direction, F net x equals max. Another time for the y direction, F net y equals may. We had our 2 unknowns. Our unknowns were Fa and Fb. And we had our 2 equations. Our 2 equations were F net x equals max, F net y equals may. We had 2 equations with 2 unknowns, so we were able to solve for everything.